So, this project's a few months old now. I wanted to talk about the uh, the principles that went into building it. There wasn't a name for it when I started, or at least I didn't know there was a name for it. And this reminds me a lot of the scene from Tropic Thunder where Nick Nolte is asked what kind of gun he has, and he says, "I don't know what you call it. I just know the sound it makes when it takes a man's life." This is kind of how I feel about patterns as well, meaning like a lot of the time I'll be using patterns or I'll see other engineers using patterns. They don't know the name of the pattern. They only know what kind of job it can do for them or how it solves the problem for them. Which is totally fine because I think the whole point of the emergence of cataloged patterns, like in the Gang of Four book or whatever, was that you wanted to see the things that developers are commonly arriving at for how they build systems and kind of put a name to the things that they're seeing, rather than for those catalogs to be sort of the authoritative source for how developers should do things. So basically, the approach to how I've done Argyll is called functional core mutable edges. The way that I thought about it when I was working on it was just, hey, I don't want to allow for any mutable state. I want to rely on determinism in functions, pure functions, meaning for any input, it should map to a single deterministic output always. Also, my thoughts were that the system itself should be capable of being described in terms of being kind of a single function, meaning you have sort of your initial state of the entire system itself as one argument to that function. Then you have the command that you want to apply to that initial state. And you also want to have that command applied at a specific time. And given those three input arguments, the system itself should act as a deterministic function and yield kind of state prime, the resultant state from having applied those three input arguments. So the idea there was that you have the only way that you could implement that would be with events. Also with patterns like command query responsibility segregation. So the idea that you should be able to read the state in kind of an asymmetric way than the way that you would apply commands to the state of the system. I also am a big fan of persistent data structures. I think that's Rich Hickey's fault for having me have to use them in Clojure, and so I tend to use them even if I don't have to, because I feel way more safe writing algorithms or implementing algorithms with them. So as we look through some of the code in Argyll and specifically Timebox, which is the event sourcing library, one of the things that you're going to find is if you told Claude or some other tool to say, hey, I want you to analyze this project and tell me all of the places, excluding things like caches and sort of mutable schedules, which have to be capable of mutating, tell me where you see in-place mutation of structures. And I've done this actually, about a month ago or so, and it basically gave me a list of maybe like one or two or so. And quite honestly, so as you go through the code of Argyll and Timebox, you're going to see that in-place mutation of data is very rare. You're also going to very rarely see mutexes as well, because I almost never use them. I tend to prefer higher level Go abstractions like channels and Go routines for sure. And there's just very few cases where I actually do use mutexes. One of them I showed last week, and that is in the event itself. So the ability to be able to create a memoized field in the event to avoid excessive marshalling to and from JSON. But other than that, you're not really going to see it. You are going to see patterns that if you've ever coded with like the flux pattern on React, that look a lot like that. And then the interesting thing is that when, back maybe about 10 years ago, when I was trying to explain event sourcing and CQRS, these concepts to my backend developers, and they weren't really grokking it, I said, the interesting thing is that our front enders already sort of internalized this mindset, because in React, if you're using like the flux pattern, it's almost unavoidable. You have to do things like you'll see structs where, not structs, but like objects that are being constructed from other objects using the spread operator, and then only changing the properties that need to be changed. If you look at the Argyll source code, you're going to see the same pattern applied, just done in Go. That's pretty much it. So what I'm going to do first is I'm going to kind of give you an idea of how Timebox works. I'm not going to go too deep, but because it's event sourcing, so I don't have to go crazy with the idea of event sourcing. But at the core of event sourcing, you have the idea of an aggregate that where everything is sort of applied from the root of that aggregate, and the aggregate sort of just accepts events being applied to it in this case, it's a very opinionated library. I've sort of mashed everything together because that's what I needed. So the aggregate itself is doing its own internal projection. If you look here, right, there's your internal projection value of a specific generic type. The good thing about Timebox is it lets you sort of just define what that happens to be. You would register some appliers, and what that means is that the idea of an applier is, given a projection of t, it will accept an event and use that event in order to create a new version of t. There's your functional abstraction there, right? If you look down here, this is it. I mean, it's pretty straightforward, right? Func takes a t, also takes an event, and returns a new t. That's the abstraction. Super straightforward, super simple. Then you have an ID. The idea of the ID is just the aggregate ID. That's how we know how we can persist things and identify things. Also straightforward. Within the aggregator itself, we also have enqueued events. And the idea with enqueued events is that as we're making changes to the projection, we are basically raising new events. We're not modifying the projection ourselves directly. We only will modify the projection based on events and how events are applied to the projection. So the idea there is that you will raise events and they become enqueued. And they remain enqueued until you use that aggregator to sort of successfully take that new state that you're satisfied with and flush it to disk. Now, the underlying mechanism of the backend basically says, if I can append these events, because the tail of the event stream is exactly where the incoming aggregator expected it to be, which is next seek, right? You can see it right there. Then it will accept those events being appended to the stream. Otherwise, it'll kick it back with a version conflict. So that's that. At the end of all that, when you want to flush those things to disk, it basically ships all of the events that had been enqueued and puts them into the flushed slice. Now, the way the mechanism works is that it allows for things to be flushed multiple times. Generally speaking, that's actually not even the case. It will just do a straight copy of what's enqueued and just call it flushed. And the reason why we need flushed is because at the end of an executor that is taking an aggregator, we want to know all of the events that had been successfully appended to the event stream itself. Next seek, like I said, this is basically the idea is that we already know what we believe to be the end of the event stream. And so everything that we do is going to be based on that, meaning even the initial state of value is based on that as well as a projection. It could be that it's not, but generally speaking, the idea that it is. And then at the end, if it all is successful and we do have any real world side effects, like, I don't know, sending an email or whatever, whatever it happens to be, we can, in the meantime, enqueue success actions. And a success action is just, that it's the final state of the projection, and then the all of the events that were used in succeeding in that execution. Pretty straightforward, but it makes more sense when you actually see what an applier is. And so what I'm going to do is I'm going to go into the Argyll code so you can kind of see that, right? And so in Argyll, this is a list of all the events in Argyll for an entire orchestrator. And the irony there is that there's not that many. I think there's 18. I didn't count it. As I recall, there's probably about 18. What we're interested in is flow started. So event type flow started, that's going to be raised, you might guess, when a flow has been started, right? So we have the plan, and we basically want to signal that the flow itself has begun. That hasn't done any work yet. Work actually happens when the executor or the processor of the flow says, what do I actually need to do in order to be able to be successful at achieving the goals of the flow, because that's how the model works. And that means that it will identify any steps that it can start in parallel to sort of kick things off and start moving the workflow toward its final conclusion. That's done through step started. And the thing about a step, again, is that a step itself may actually spawn many work items because there's like 4 each. And so that means that for any input that it takes, it may actually explode that into some kind of a Cartesian product and work on it in sort of a parallelized way, just spawning many little workers to do things and then collecting them all at the end to call the step completed or failed, depending on what actually happened. So those are the events. We don't need to get too deep into them, but as you can see, event types are just strings. That's how we're identifying them. If we go back to the appliers, because one of the things about appliers, if we go back here, is that an applier is just a single applier, right? And what we really need are a set of appliers, which is a map from event type to the applier itself, so we know which applier to actually use to apply the event to produce a new state. And how appliers are used is actually to be passed into what's called an executor. And so the idea of an executor looks like this. So it's basically just, again, it gets the generic, right? It's attached to a store because the executor needs to know how to persist or retrieve events to do the things that it needs to do. It gets its appliers, so it will always use the same ones. It gets a constructor, and the reason why it needs a constructor is it needs to know potentially how to create an initial state of the projection if there are no historical events there. So that would be just sort of like the starting point of a projection. The idea is like you might want to create like empty hash maps and stuff like that to just seed things. There is also a cache. This is basically a last recently used cache. So the idea is that there are a bunch of projections that it's using. The cache itself may want to pull hot ones back so that it doesn't have to keep going to the database to optimistically know what it needs to try to work on. So that's what the cache is for. And there are what's called initial success hooks. So the idea there is that when you create an executor, you may have some sort of like background success actions. Like, for example, for any executor, no matter what happens at the individual command level, you always want to call this success action. Maybe for publishing or for logging or something like that. That's what that would be used for. Executors take a command, and a command is basically the initial projection, and then also an aggregator instance. And why the aggregator instance is passed into the command is because the executor is managing the aggregators. It needs to be able to create flushed ones and throw things away so that the next time your command is run, it's always basically from the point of view of being a clean slate. It doesn't try to make it so that you have to think about, oh, well, the last one failed. What do I do about that? The executor deals with that. It just basically starts things over. If there's a version conflict, it fast forwards so you get a good copy of the current projection. And so everything is basically clean. That's that. There's your projection. It's just the state plus the next sequence. So like this state is based on that sequence. And if it's off at the end, you get your version conflict from that. That's basically it. Then you get the exec. So, the idea there is that you want to execute against an aggregate ID inside of the store, and you give it a command to run, which you implement yourself. But the executor does a lot of work in the meantime before it even potentially calls your command, right? And so the idea then is that you have a for loop up to max retries. So you can configure it so that it doesn't try more than 10 times to deal with like version conflicts. If there's a natural error, then it will just bail completely out. It won't retry. Max retries is only for version conflicts where it knows that it just needs to fast forward and get up to speed to make sure that it can properly apply the events that you hopefully yielded in processing the command. Then it creates the new aggregator for you with some initial state and so on, right? Then it calls your command. And what you're going to see here is ag.value. So this value is always retrieved using the method. And the reason for that is that it does change over time. So whenever you apply or whenever you raise a new event inside of the aggregator, it will apply that to the projected state, create a new state. And the only way to safely access that is through the function rather than keeping a reference to the original state that you got. And the reason for that is because we don't mutate in place. It's very important because you don't want to have stale state, and even more importantly, you don't want to mutate something in place that is cached. And then from that point on, everything, even if you're unsuccessful, especially if you're unsuccessful, that from that point on, everything that tries to use that state is going to get a broken version of it. So it's a hard rule that never happens in the system itself. So we run the command. If there's an error coming from the command itself, then we just return that error. After that, we say, okay, well, the command was successful from just a purely programmatic logical point of view. Now we're going to try to flush all of the events that it raised to the store itself. And the idea there is that if it can do it, given this callback here, it's going to append those events to the store, and they may return an error, version conflict error. So if there is no error, what we want to do is we basically say, okay, well, there are no events that were actually raised, which can happen. You may actually run a command that is a query. So it doesn't actually mutate, but you still want the query to give you a consistent view of the database. And so it raises 0 events. And it may even have side effects. That would be totally acceptable as well. And it just returns the state as is. That's the idea. If that's not the case, then you get the current value. And what you're going to end up doing is you need to update the cache version of that state. And then you're going to do the run on success, and then you return everything. That's kind of how it works. But if there is an error, which is this fall through here, specifically you want to check if it's a handle version conflict, meaning like if you can't handle it as a version conflict, then you actually need to return it. And so that the ultimate caller knows that it can't do anything because the number of retries has been exhausted, which is right there. So that's that. I mean, that's from a high level, that's it. Now, what I want to do is I want to show you the way it's done in Argyll. What's a good one? So let's try flow state. So here are the structs, right? So this is how these structs are how we represent state in Argyll. You have your like catalog state, and the catalog state is pretty straightforward. It's sort of like it's a monolith, kind of like a singleton that has all of the steps that are registered against the system itself. And then all of the attributes that have been pre-digested as a graph. The reason why is that you don't want to have to sort of digest all that stuff over and over and over again. If you can pre-digest it based on the changes to the steps over time, it makes it much easier to generate a plan, right? So this is basically, it's a speed up. You wouldn't necessarily need it. It's not absolutely necessary because you can derive that from steps, but this just makes it a heck of a lot faster to be able to understand like how you can achieve a goal through the graph that's created from the relationships between all the steps. Then you have your partition state, and the idea there is that any partition within the cluster, because we're now officially a Raft cluster, I've gotten rid of the Redis backend. The main branch of Argyll is now using Raft directly with a segmented Raft write-ahead log that I designed, and a very lazy snapshotting system, meaning like I don't proactively create snapshots, and the reason for that is because we're using bbolt under the hood, and a nice feature of bbolt is that you literally can tell it to create a hot backup that's a read-only backup just because of the way the data structures in bbolt work underneath, and it's basically a zero cost backup. It's really, really cool. So you call it, and then you get like a byte stream where you could just write that over a socket as your snapshot to any peers that need the snapshot. Will it get really big over time? Yes, it will. I've got to address that at some point in the future, but the mechanism itself is actually kind of sweet. But any single partition, right now, the only thing it's tracking is its own health. And by that, I mean the health, its understanding of the health of the individual steps that it's connected to, because obviously you may have real partitioning, right? Where one partition or node in the cluster can't reach a step, whereas another node could actually reach a step. And so we need to be able to track that based on all of the nodes in the cluster. And what I may do in the future is I may use this to be able to sort of do like workaround routing, meaning if one node can't reach a step and that step happens to be in one of the flows it wants to achieve, it could basically just redirect that execution to another node that does have a healthy path to those steps, but I'm not there yet. That's for the future. The most important thing though is this. This is the flow state. Now the flow state has most importantly your plan, which is your execution plan, and if you want to take a look at that, that lists the goals that you initially asked it to achieve, and then the required arguments that it needs in order to actually even be able to start. It's already identified those, meaning like if you create a goal or multiple goal steps, it's going to analyze the graph, and based on what the graph shows, it knows that a lot of the attributes might be able to be satisfied from upstream steps. What remains are the attributes that just absolutely have to be provided via the initial state of the flow. So that's how that works. These are the actual steps that are going to be used in achieving the goal. And the idea is there is just a map step ID to step. The reason why they're part of the execution plan is because one of the early design decisions that I made about Argyll is that, yes, you may create an execution plan based on the graph as it currently exists in the catalog, but you shouldn't be excluded or precluded, my English is bad, from programmatically creating an execution plan based on steps that you're dynamically defining at runtime on demand. So for that reason, that's here. It also definitely helps with avoiding to have to maintain multiple versions of steps over time, because once that execution plan is created, it's snapshotted, it's there forever, and that is what that single flow instance is going to operate against from that point on. Here's your attribute graph. This is basically a culled or pruned graph. Only the attribute node edges that we need. And then the list of excluded steps that are excluded for reasons that the initial state may have already been provided. I think that's the logic. So based on things where an attribute has already been satisfied, or it's missing from the graph and just basically impossible for those steps to ever be reached based on the way that the graph is composed. That's kind of the idea there. So that's your execution plan. Let's go back real quick. Then you have metadata labels. This is just so that you can search labels, so you can search. Metadata will have information, for example, like the webhooks and stuff like that, like the base for the webhooks. Some more metadata, like when was this flow deactivated at. These are the executions, and what executions are is like this is how it actually tracks the real work that it's doing and the current state of each work item that it may have spawned when it hit a step and started a step. The overall flow status, and the idea there is it deactivated, is it running, or so on. Possibly an error if the flow ended in an error state, and then of course the ID itself, the unique ID of the flow. If you want to mutate these things, you can't just mutate them in place. You're not allowed. That's just not how the system itself works. And so the way that we mutate them is, let's see if I can find flow state. Here's some methods. So get attributes, that's a reader, right? So you don't have to modify anything. You've got it. But if you want to set status, you're going to see this pattern a lot. And here we're going back to the whole Redux flux pattern stuff. So if you want to set the status of the flow state, you give it a new status, and then it returns a new flow state. It doesn't change the same one in place. And in Go, the way that this is done is that there's a couple of ways to do it. I do it like this. I just think it's cleaner and nicer to look at. Is that here you are doing an indirection of the pointer. So res now is a local copy of the receiver flow state, meaning like it's right on the stack. It's created the entire thing as a copy of the original flow state. So it's a shallow copy. That's the beauty of it, yeah. Based on that shallow copy, you're now setting the status to the new one, and then you're returning a pointer to the shallow copy that is on the stack. Now in Go, if you know about Go, the way that it works is that it does exit analysis, meaning if you have something that's a var. So for example, I'll just give you a kind of an example here. If I said this, var res flow state equals, like this, which is basically what this is, right? What I'm saying is I'm creating a var on the local stack, and it's of type flow state. You'll notice that it is a concrete. It's not a pointer to, right? And then I'm going to assign it to -f. And the good thing about Go is that you don't have to explicitly say, oh, well, actually, this needs to be a pointer because I'm going to be returning a pointer to it. Go is smart enough to know that if you have something that is a concrete value on this current stack frame, that it is capable of actually allocating this on the heap because it knows that a pointer is going to escape from the function call. So you can do that magically. It's not like C, where you would have to do the work explicitly, which is kind of nice thing about Go. So that's the pattern. You set it, you return a pointer to the shallow copy that you made, and you're going to see that pattern everywhere, right? It's pretty repetitive. It's very boring, but one of the nice things about boring is that it can be very safe, and that's exactly why we're doing this here. So, throughout the entire system, what you're going to see is patterns like that. Very, very little in-place mutation of data. And the benefit of this approach to coding is that, here's where we get into AI, is that tools like Claude and Codex, they actually do a hell of a lot better job of reasoning about code like this than they do about code that is doing in-place mutation and that is protected by, synchronized keywords or mutexes and stuff like that. It's very hard for it because it has to work temporally at that point. It has to know, okay, wait, let me think about this. If you lock this here and this is called there and this may be called afterwards, and I don't know when they're really being called because I don't have enough context to ever truly understand that, then it's going to break down in its ability to reason about that code. But when you apply patterns like this, where you literally say, hey, this is a function and it takes an input of flow state. And by the way, in Go, magically under the hood, A receiver is just the first argument to the compiled function. That's what it looks like under the hood in Go. It's just sort of an implicit first argument, like a lot of other languages actually. And because it's going to return a flow state, then it can reason about the fact that it knows that you have sort of the input flow state, and then you have flow state prime, the modified flow state. And based on what it sees in the code, which is again very simple and very easy to reason about, it knows that it's actually doing something where it doesn't have to worry about concurrency on those data structures. And when it creates tests and when it does refactorings, it can do a hell of a lot better job with safe refactorings doing this rather than going the path of like, I've got mutexes everywhere and this is how I do things. I'm trying to save memory by just keeping one instance of everything and then like synchronizing that one instance. So yes, downside, you create more RAM consumption. Upside is that you have far fewer lock granularity, and so your concurrency actually works relatively well. That's one of the nice things. And a good upside, again, is that AI does a good job of actually reasoning about this stuff. One of the things that I've noticed is I have another project that I don't ever talk about because I feel like it's a failure, is that I used AI to generate that as well. I did not apply these patterns at all. It was sort of more of a traditional approach where I have a lot of locks and stuff like that. And what I found is that it does a terrible job of maintaining that kind of code once it started to get pretty big. When it's small, it can reason about it because maybe there's just sort of enough enough of a window that it can reason about those things. But the larger it gets, the more it breaks down. With this pattern, sort of the functional core pattern and mutable edges, it can go much longer reasoning about that code, meaning you could, in theory, pull in a rather large repo that uses this approach, and your AI tooling would have no problem reasoning about exactly what it's dealing with, and being able to make safe refactorings to it. So that's the benefit from an AI point of view. And like I said, this is completely built with Claude and Codex. I've done some manual coding, not much though, quite honestly. I think what I tend to do is like, I get dissatisfied with what Claude produced. I tell it how to make it better, but I almost never take my fingers and put them to lines of code. But that's the pattern. You'll see, it's just everywhere. It's just the same pattern over and over and over again. Super, super boring. In theory, I could write a Go generator that just does this. But this was done with Claude. And the way I did it with Claude was just to say, listen, we're applying this pattern. This is how we do mutation to structures. This is how you write code to be able to generate that stuff. And it did a relatively good job of it. So that is that. The other thing I want to do is I want to go back just so you can see how make appliers works. And I think I can't remember exactly where I did that. It might be in Flow. Yeah, here we go. So the idea is that I talked earlier about appliers, right? And for flows, what we want to do when we create an executor so that it can actually apply events to an aggregator that was connected to the callback for the command. You basically just want to map your event types to an applier, and the way that it's done here is that there's a function called timebox make applier, and I'll let you see it real quick. It looks like this. The reason it's a top level function is because it takes generics, and the only way to allow for multiple different types with generics in Go is to actually do them as top level functions. So like once you've created an instance of a struct type that has a generic attached to it, you're done. That's it. It's concrete at that point. And so the idea here is I say make applier. I give it a function that I want to turn into an applier, and we make sure that the generic is there. And this is your projection type, your state type. You give an event that's just a normal time box event, and then you have your data, which is the data that is used to actually create that event. So the underlying payload. And so if you look, so I get the event value, and I talked about a get event value last week. So this is the event, and it has its own internal payload, which is that raw JSON that I described. It gets that successfully, and then what it does is it calls your callback function with the initial state, the event itself, because it might need it for some reason, and then the actual data that it demarshalled. And that's pretty much the idea, so that you can call an applier that takes the real type and not have to do a lot of like type checking and stuff like that. It just makes it much cleaner. So if we go back, you can kind of see what I mean. So like, for example, we just have normal functions here, like flow started, right? So if I look at flow started, it's going to take the initial state, which we don't care about, so I just ignore it, take the event, and then for data, it's going to take the flow started event, right? And flow started event is just that. It's a normal struct, and because we are using generics and being able to do like a get value based on that generic type, it's a fully materialized Go structure. And that's how the appliers work. Now, obviously, there are many of these, but what you're going to notice about them is that, for example, well, ignore that. That's creating some basic executions, because it knows flow started is sort of the kickoff event. And so create executions takes the plan and sort of pre-populates the executions it's going to need to do to be able to run things. But other than that, it's just setting things up. And then it's returning the flow state itself, which is your kind of your new state after the application. We don't have the initial here because we don't actually have any initial state. This is the kickoff event. Then I'll go back. You can see, where's a good one that might be interesting? How about work? I don't know, work started. Work started, again, these are pretty simple, right? All they're doing is saying, hey, I need an execution. Get me the execution for step ID, right? And if you look here, by the way, it's a work started event. So it looks like this. The flow ID that we're talking about, the step ID that's being targeted for work or started where work started. A token, and a tokens are used to be able to complete work asynchronously, because what happens with any single work item is you may call an external HTTP service, and that HTTP service may actually call a webhook much later or return immediately. But in any case, the way that the work is completed or failed is via a callback based on that token. And then also the work started with the inputs that it was given in order to start that work. So that's what that looks like. So it gets it. It's not doing any checking here, and the reason why it's not doing any checking is because it doesn't have to, because executions was already populated earlier. And then after that, you basically say, I've got the work items for that step. Get me the specific item that I'm looking for, which is... So I'm actually setting the status. So this is actually a new copy of that item, right? So because I've started work, I want to activate that work item. So basically the pattern here is like, I've got the exec. I'm looking for the work item that's associated with the token that we got from the event. And I want the item to have a new status of work active, because now work has started. That's basically the idea. Here, another thing that we're doing is that we're saying, listen, if the item doesn't have a started at, we're going to set a timestamp, basically. And that timestamp is coming from the event itself, which is there, which is why we need to take the events as well. And then at the end of all that, we're returning the initial state with a new set of executions based on what we had already done. Set work item with the new item based on the token, and also a set last updated, which is basically last updated at the current event's timestamp. And again, from an applier's point of view, you're going to see that pattern everywhere in time box-based apps, and especially in Argyll, because this is the way that Argyll works. Argyll does not mutate anything in place. It needs to be incredibly safe. It could be, for example, that, there's contention, there are multiple events coming in at the same time against a specific flow, and it needs to be able to accept those commands without causing chaos by mutating the same data structures in a competitive way and just acting like, bad neighbors. So this is how it all works. Is it harder? Yeah, I mean it's harder to be disciplined about this stuff. But is it better? Yes, absolutely, totally better for the reasons that I've already stated, and it's something where I would highly recommend investing in this approach. It doesn't have to be pure functions. Like you don't have to write things in Haskell, right? The point is to take some of the learnings from functional programming that were valuable learnings and apply them to ways that we code in systems programming languages, for the reason of creating safety around highly concurrent code, which in this case that's what we've got and that's what we're dealing with. And so yeah, there you have it. The ideas of functional core, mutable edges is highly valuable. It's, I would say it's not even that important from the point of view of only AI. I think it's a really good approach to developing systems that are capable of scaling and being safe. But from an AI point of view, I have found that it has been kind of almost a godsend, where it makes it just easy to maintain really large code bases, and not have the code generator just blindly screw up the code because it just can't reason about what it's looking at. It does a really good job of reasoning about this code. So think about it, apply it. It could be a valuable way to do your work. And yeah, with that, like I said, the one news that we have for this week in Argyll is that the main branch is now just using pure Raft, and I'm going to continue to massage the Raft backend, so it gives some of the properties that I would like. It's very safe right now, very resilient. It's conservative about compacting, so it only compacts kind of when it knows it can, because it wants to avoid unnecessary snapshots. It also will not proactively create snapshots, which is also good because Bbolt is great in that it really can do this hot backup thing, which is amazing. What I'm seeing from a performance point of view is that it can do about 4,400 flows per second on my MacBook Air 15, which is an M2. Which, for a Raft where you're writing, 3 logs at the same time on the same computer, that's not actually that bad. I also have found that the SSD on the Mac is the bottleneck. When I tried these same tests on my little B-Link Ryzen 7 mini PC, it was actually much faster because of the disk. The NVMe on that computer just smoked the SSD on the MacBook. I have no idea why. Maybe Apple's more conservative about doing flushing. I have no idea. But for sure on the Mac, the I/O is your bottleneck. But even with that bottleneck, the number of flows per second is actually not that bad. And it's maintained over time, which is also quite nice. But again, not ready for production. Don't use it for production. I'm gonna get there. I think. Give me a couple of months, and then I'll say it's time for people to actually really use this, because I'm gonna break stuff in the meantime. I promise. All right. Well, with that, have a nice week, and I'll update you again probably in 2 weeks because I have to take vacation, and so I'm gonna be gone next week. Anyway, thank you.